In semiconductor industry, we have a bunch of data, but there are also some challenges there. And Anja will talk about how she tackles these challenges on a daily basis. Please welcome on stage, with the title of her talk, a wide range of opportunities for data scientists in the semiconductor industry, Anja Zernig.
Thanks a lot, Andrea, for these introducing words. I'm very happy to be here, being also part of the organizing team, but it's a pleasure for me today to let you know and give you some insights about data science and the possibilities in the semiconductor area. Yes, why semiconductor industry? As Andrea already said, KAI is a 100% subsidiary of Infineon, one of the largest semiconductor manufacturer worldwide. And we are located really right over there, next building, close to this one. And we are a research center on different fields related to the semiconductor industry. And as a research center, we do also have a broad national but also international network of different partners. This comes because we are participating in different funding projects, but we do also have a lot of students at KAI. And actually, we are about, or currently we are even more than 70 employees, and half of them are students which are conducting together with us in an applied area and atmosphere their master thesis, PhD thesis, bachelor thesis. And this is also why we then have good communication also to the industrial partners via our students at KAI. This is currently our team. We are 14 people, and also here, half of them are students supporting our project work in different areas like image classification, pattern recognition, anomaly detection, job scheduling, computer vision, equipment monitoring. These are just some things and the main buzzwords we are currently dealing with. But having now some focus on the semiconductor manufacturing line, I want to show you some use cases we are currently working on, and also the related data sources where you have different possibilities and different methodologies you can apply. And in semiconductor industry, it's divided into a front end and a back end part, where in the front end, everything is about the wafer. The wafer enters the production line, and due to different process steps, it's then finally processed and tested the first time regarding the functionality at the wafer test stage. And as you can see, if it then goes further at the dicing, we're just further sending the good parts, because we already scrap out those devices which are not functional. And after this one, every device is getting a package on the one hand, because we want to save the device from environmental influences, and this is then also more convenient to be plugged in into other applications. Of course, also afterwards, we test it again, because we want to ensure that we just sell high quality, and if we are sure that the devices are working well, then they are sent to the distribution center and are ready for our customers. Having now a closer look on the data, and first starting with the front-end side, where I said, okay, a wafer is entering the fabrication line until it's finally processed. And along this line, we do have different data sources providing different possibilities to gain knowledge and value out of it. One data source, for instance, we are using for fault detection and classification, advanced process control, and this is data coming from the equipment itself. So the equipment is equipped with some sensors, and these sensors are recording parameters over the time during the wafer is processed. This could be, for instance, the temperature in an oven, or some other parameters like gas flows, gas concentrations, and out of these signals, you can calculate statistical values, simple ones like the maximum, the mean, but also more sophisticated ones using LSTMs, methods from the area of signal processing, time series analysis, so you are quite free in choosing whatever helps then in the end to keep your process under control. And same for statistical process control. So you take samples out of the production line to also check whether, for instance, the thickness of your wafer is still within predefined limits or not. Here we're just dealing with sample data because we cannot always measure everything, and this is also not needed because we have methods in place which can provide good predictions and provide insight to the whole area then in the end. And one data source I want to focus a little more onto is coming from the defect density area. So we are always interested in how many defects are present on our wafer. Yeah, although we are working in a clean room environment, there could be some defects, and this is what we want to measure, because of course, if we have too much of them, we have to take countermeasures. And to take the correct countermeasures is even more important, not just the number of defects you're detecting in there, but also the type of defect you see in there. And to evaluate the type of defect, along this production line at predefined steps, high-resolution images are taken, where you can clearly see which type of defect is present in your data. And state of the art is that you do that manually. So there are operators in the line having a catalog and checking and classifying then in the end these images into their corresponding defect classes. And this is the perfect scenario to start a data science project with, because we have here a lot of labeled data available. And of course, we want to automatize this by training a machine learning pipeline which is doing this job in future then automatically. Here we do also have some challenges. One of these challenges is that we have a highly unbalanced data set. This is quite natural, because some defects just occur more often than other ones. So we have to consider this for sure in our analysis pipeline. And also another area is what happens if new defects appear, new defects which you haven't used for training your data. How can you react on it? How can you monitor your system and be aware as soon as new defects occur? Some results on this one. You already see on the left side the one experiment which provided the worst results, and on the right side the best ones. And I want to show you how we achieved this coming from a worse classification result to a very good one. In that scenario, we focused on the data. So what we've done is we kept the CNN in the back, we kept it fixed. We kept the structure, the hyperparameters, everything, but we worked on the data itself, we inserted there. And although I told you beforehand we are aware that we have unbalanced data set and we know as data scientists that this is critical, we just did a test. So we didn't do any kind of transformations, additional information, something like this, just to know what's the baseline we are starting from. And as you can see, quite clearly, no validation accuracy is not very satisfying. So what have we done as a next step? If you are in an unbalanced situation, you can try to apply class weighting. So you give to the majority classes minor weights and to the minority classes higher weights. But as you can see, this was not the way to go then in the end, because yeah, the results didn't increase. Then, very prominent and also very powerful is data augmentation. Data augmentation means that you're taking your original image and you're doing some transformation. So you artificially increase your data set by doing these transformations, and then you have some additional labeled data available with which you can train your model. But also here we didn't see an improvement, because we still kept the number of samples in each class fixed. Now comes the good news. The best combination was then in the end doing resampling first, meaning that you are oversample your minority classes, undersample your majority classes, and do data augmentation in addition. And as you can see, we had an improvement of 20%. And this is quite interesting. And also for future data sets, because we encountered, okay, maybe it's better to split one or the other class into more classes. And with that, in the end, or by today, we now achieve a model with accuracy of 93%, just by working on the data. Always the same network architecture in the back. And yeah, it's known as the data-centric approach, which really brings value to your results. And also my former speakers talked a lot about the importance of data, and so do I. Yeah, on the one hand with this example, but I also have a story or some thoughts in that direction to you, which I want to share. Because you might all still remember the sentence, which already appeared, I don't know, 5 years ago, where it was said, data is the new oil. And actually, what was meant is, with data, we can create knowledge, and knowledge is power. But I also find another analogy to this one. If you say data is oil, yes, because you need oil to keep a system running fluidly or flawlessly. And same for a machine learning pipeline. Good data is important, not always more data. If you have good data and more of that kind, yes, but it's really important to have high quality data, like having high quality oil for your system. Coming to another data source, we are here already at the stage of wafer testing. So this is the first stage where you can test the functionality of each of your devices on the wafer. And if you visualize these electrical parameters which are tested at that stage, you can see them as so-called wafer maps. And what we are interested here is we want to do some pattern recognition. But as you can see, nearly every wafer map shows some pattern. So what's important here is that we really just want to focus on some of these patterns. Patterns which are somehow critical, which you want to be informed of as soon as they appear. And currently there's no manual inspection in place because it's still not feasible. You can imagine that for one wafer, dependent on the product you have on there, you can have 10 or hundreds of parameters, and doing this manually is still not feasible. There are other methods in place which you can use for doing so, but here is just the goal to speed up this process and be informed via training a machine learning pipeline, that you then just be informed about the occurring critical process pattern in the end, acting as a decision support system. And you might also know these discussions between what model should you use. Should you use a machine learning model or deep learning pipeline? And we as data scientists, we know what the pros and cons are. But at least in a scientific field, you can always say, let's try it out, let's find out which works the best for our model. And we have various possibilities, of course, on the machine learning side, where we can choose between different pattern classifiers, but why not doing an ensemble out of them? So you can do really a lot of different combinations. And if you don't know, but have the time and the computing power, you can try out different combinations. And on the deep learning side, it looks similar. And also here, we compared these two approaches, and in the end, they performed same good. It's just a question where you want to put your working emphasis onto it. And as another example, now we are already in the backend side at testing. It's about anomaly detection. Here we are already dealing with the packaged devices, and you can see here anomalies like missing ball, missing bed, or also a bent lead. And the challenge here is that these failures or these anomalies do not happen very often. So here we are even in a more unbalanced data situation. And this is also done manually currently, and what we want to train a model for, not just having a model in place in the end, but a whole machine learning pipeline, including also a GUI that the end user can then apply this model on its own to make this evaluation and to report on the detected anomalies on there. Challenges, one of the first ones, is that we don't have images from each of these devices in place, but we get a whole image from different devices in the so-called tray. And first step is to train an object detector to extract the images of the single devices. And since we are in the area of anomaly detection, we are training a model just on the good parts, because then if we're inserting some with an anomaly, this should be then visualized in the results, as we, for instance, have it here. So on the left side, you do see the original image. Hopefully, you also find 4 missing balls. And on the right side, it's the result from the model. And if you compare it, they have been detected. And also, of course, some other things which are just anomalous in there. And what we have to keep, not just for this use case, but for every use case in mind, is that we live in a constantly changing environment. nothing is static, so AI. And therefore we have to react also on new circumstances. New data is coming in, new products are produced. New products mean new data, new patterns, new anomalies, new defect classes. So we have to keep this in mind, that we are living in this constantly changing environment. We have to keep this in mind already during development of a machine learning pipeline. And I talked now a lot about data, about challenges and use cases, but in the end, AI is from people for people. And this is something which I think, due to the hype of AI, is sometimes forgotten by the audience, or by the end customer at least. Yeah? I sometimes have the impression that they have the hope that one data scientist will save the world. But in the end, it's a group of people working together, and this is why I do like really just the first sentence of the Wikipedia entry about data science, where it's written data science, it's an interdisciplinary field, not a one-man show or one woman, one person show. And yeah, meaning that different parties are involved in such a pipeline, in such projects. On the one hand, it's the industry with the needs to solve some problems. On the other hand, we do have the academic world. And in between, we have the bridge. And I, as an employee of KAI, I do like to see myself as a kind of translator, as a kind of, building the bridge between the industrial needs and the academic world. Because on the one hand, we have insights into the needs from our customers, into data, into production issues, into different circumstances from the industrial side, but on the other hand, also having the models in place, applying them, but being also in close contact with the universities. And just to mention some of them, for instance, University of Klagenfurt, I also saw Professor Jürgen Pilz today with us. He's already Professor Emeritus, but he's currently also external lecturer here at the Carinthia University of Applied Sciences in the study program of Applied Data Science. And the head of the study program you also visited today, he's outside at the registration desk. And it's always very good to collaborate and to cooperate with such smart people. I'm always happy about that. And what I also want to mention is, similar to KAI, there are also other research centers we are collaborating with. On the one hand, the No Center. Something about No Center we will also hear in the last talk of this session from Angela. And I also want to mention a currently very good running collaboration with Fraunhofer, more specific with KAI for Life. The head of KAI for Life, Ega Egerling, is also with us today. She's going around with the microphone, taking your questions, and also learned to know already some other colleagues from there. Yeah, just as an example of a very good collaboration. And if you now think, wow, that's cool, I also want to get in touch with KAI, with Infineon, with the people in there, let me know. I will be here the whole day. Also, a lot of my colleagues are here today. And in general, KAI and Infineon are always searching for good partners for projects, or also for new employees. And within Infineon currently, there is a project running which is called IPSE, a quite cool name because it stands for Important Project of Common European Interest. Yeah, a project where different companies collaborate with each other. And Infineon has a special focus in this project to do communication, to find new collaboration partners, cooperation partners, performing industrial workshops to get in touch with small and medium enterprises, startups, large enterprises, but also workshops with the universities to get in touch with professors and researchers. And if you're a student, you might also be interested to be an internship at Infineon or KAI. And if you're already PhD or you want to do a PhD, please also ask us for the PhD program. We have a very cool PhD network within Infineon, where you also have then the visibility within the whole company with your project. And just to the end, I want to say, maybe this is the answer today for everything. Communication is really the key for a successful project. So let's communicate, let's come to me afterwards, talk to me in the coffee break. I would be happy to be in contact with many of you. Thanks a lot. Thanks for listening.
Thanks a lot for your talk. Anja, now I'm motivated. I want to join your team. What should I bring with me? Which unique selling point are you looking for when I can say, yes, now I'm prepared to be part of Anja's team?
As you said, if you are motivated, this is the first step, and then we can see, because, yeah, data science itself, as written on Wikipedia, is an interdisciplinary field. So you do not have to be always an expert into the modeling part, but if you more focus on data engineering or in that direction, or if you're a good programmer, but you like the idea of programming something in the direction of AI or where AI is used, just let us know. There is not the specific study we are searching for. It's really your motivation, your own attitude, your favor for the topic in the end.
Thanks a lot again. Please lead Anja again with an